These are the outlines of my talk where I will briefly introduce you about the modern liquid crystals and what experiments we are currently doing here. Basically, I will introduce only one charge carrier mobility measurements, which we are doing principally at this institute. I will also introduce some of our most recent results and future scope in this domain. So before I go to the physics and change your test from theoretical to experiment, I would like to introduce my city. So you can see here, these are the four beautiful views of my city. The city is known as Calais. This is one of the famous place in northern France, which is one of the best center for the trade via sea route. So if you see the geography of here, so I am here at this place. This is the Calais that is close to the Belgium border, and it is the coastal city at the English Channel. So you can see here, this is the England, and this is the France, and the Belgium border starts here. So, and many of you know, maybe there is, you heard about the sea tunnel which connects this Calais and Dover, which is the tunnel beneath the sea. And this is one of the important trade way which connect to England and European Union. And my university has four major centers at four different cities, including Calais, Dunkirk, Saint-Omer, and Boulogne-sur-Mer. So basically, in research laboratory, I am associated at two places. The UDSMM has two branches at Calais and Dunkirk. So many of you know maybe a film that was released in 2000 recently, named Dunkirk, which was based on the Operation Dynamo during the Second World War. So no research work can be completed without the help of PhD and master students. So I must thankful to my PhD student, Asmita Shah, who is currently working with me, and soon she will be finishing her thesis. Vinso, he is currently working on the second topic of the PhD, and recently to Shukanya, who was the winner of Charpak Fellowship for 6 months from University of Mumbai. I would like to thank my colleagues also in my team that was previously headed by Professor Christian Lego and two other professors, including for Madhu Conference that is known as the Assistant and Associate Professor, and two research engineers in our group. So basically, maybe all of you know about the liquid crystals. So basically, you heard about the different states of matter that can be crystalline solids and isotropic liquids, as well as gaseous state of the matter. So basically, liquid crystals is an intermediate phase that exists between the crystalline solid and isotropic liquid. So you know well that all the crystals have a particular orientation and ordering, so they are perfectly ordered. So the order parameter for these crystals is 1, while isotropic liquids, they doesn't have any order at all, so the order parameter is 0. So as you know that liquid crystalline materials, they exhibit in between the crystalline isotropic liquids. So their order parameter lies between 0.2 to 0.8. So basically, there are various liquid crystalline phases in between isotropic liquid and crystalline solids. So basically, these are the nematics and asthmatics. So based on the geometry and orientation, the nematic liquid crystal have only the orientational order parameter, while the asthmatics have a 2 order parameter, 1 orientational and 1 weak positional. So the beauty of this phase is you can believe by seeing it, because we are belonging to the scientific community and we do not believe until we realize or we see directly. So when you see different phases of liquid crystals, liquid crystal molecules under the polarized optical microscope, you can get different optical texture images Okay, and by analyzing these textures, you can assign them that which mesophase is this or which liquid crystalline phase is this. So till 1977, it was a myth that only rod-like molecule can constitute a liquid crystalline mesophase. But this myth was broken in 1977 when S. Chandrasekhar from Raman Research Institute, he disclosed that not only the rod shape, but also the disc-like molecule can constitute a liquid crystalline phase. And later on, this phase and materials was known by the discotic liquid crystals. So why they are very important? So because nowadays discotic liquid crystals are used in the organic electronics based on their geometrical arrangement. So you see here, these disc-shaped molecules are arranged in the columns, and later on they are arranged in hexagonal way. So these molecules are self-assembled in the column via pi-pi interaction, and later on the geometrical shape can be hexagonal, rectangular, and so on. So you see here the intercolumnar distance between the two columns is around 20 to 40 angstrom, and the intercolumnar pi-pi distance is around 3.5 angstrom. So these molecules, they show unidirectional charge transport via hopping process, where electron or hole, they hop from one disk to another along the column. And the mobility in this type of molecule can be of around 1 centimeter square per watt second. And that is really interesting for the organic electronic applications. So why they are very important? Because the electrical anisotropy along the column and perpendicular to column, that is really very high, around 10 to the power 10. So that's why nowadays they are very important for the organic electronic application and other optoelectronic applications. So you can see here that these materials has been used in the TFTs, photovoltaic solar cells, photoreflectivity, one-dimensional conductors, photoconductors, gas sensor, and LED, and so on. Still plenty of applications remain to disclose. So now here I will include some of the modern applications and why some of the property these are important that can be investigated for the device application of such molecules. So basically these discotic liquid crystal are of semiconducting in nature. That's why we also say the organic semiconductor liquid crystals. And nowadays that has been utilized in making the OFED devices, OPV devices, OLED devices, and diodes in the pristine form, as well as in addition to the nanomaterials like different type of nanoparticles, quantum dots, 2D sheets like graphene, graphene oxide, and so on. So when we realize this structure and devices, it is a question that is mobility and molecular ordering is important of these molecules. Yes, of course, this is important. So here today in talk, I will include some of the mobility measurements which we are specialized here to do. We will cover it. So these are some recent publications on these discoting materials, which we got in collaboration with our Indian collaborators on the discoting crystals. So as you know that there are several methods by which you can calculate the charge carrier mobility. Charge carrier mobility is nothing because when you have a semiconductors, you have electron and holes in it. So when they move inside a material, they move with a certain velocity. So a certain velocity of electron and holes is known as the mobility inside the device. So basically there are different techniques known as Hall effect, time of flight method, uh, including the FIT method, okay, EL method, and the TRMC method. So there are several methods to calculate the mobility of the charge carriers, but every method have some merits and demerits. Like Hall effect, you can very efficiently calculate the charge carrier mobility in the inorganic molecules, but for the organic molecules, this technique is not sufficient. Similarly, when you can calculate the field effect transistor method to calculate the mobility, but sometimes this method is not so efficient because you do calculation and it have a certain degree of error. Okay, in addition that we recently have this time resolved microwave conductivity method, but the demerit of this method is this method gives the commutative mobility of electron holes, and if your material is impure also, so it will also include the mobility of the ions. So among all, like I really like the time of flight method for the organic molecules, because this technique is very efficient in calculating the whole mobility, electron mobility and ion mobility separately. So, you know, here, this is the Hall effect by which you calculate the mobility, and this is the space charge limited current method. You can calculate the mobility by this method as well. And you can also calculate the mobility if you are fabricating the FET, field effect transistor like devices. So many people are also preferring the space charge limited current method, but sometimes it is really hard to estimate the space charge limited current region. And many times this region is overlapped with the other region. And that's why this mobility estimated by space charge limited method, it has some error, and it always show a higher charge carrier mobility as compared to the actual value of the mobility in the devices. So in France, we have two universities, one in south of France, that is the University of Strasbourg, and second, my university, we have TOF setup. So this is the schematic of the TOF setup, where we use a Nd:YAG laser, and we irradiate a sample with this laser light. And after that, this is connected to the amplifier and voltage amplifier. Okay, and the output photocurrent response is recorded over the oscilloscope, and after that we can record the data in the PC, and we can do the data processing. So basically the principle is this, that we provide a pulse depending on the characteristic of the laser and the materials characteristic, and we can get a photocurrent response by the materials. And depending on the nature, geometry, and other parameters, the output photocurrent curve can be of two nature. Either it will be the non-dispersive or dispersive in nature. So when it is non-dispersive, it is very easy to estimate the transit time, and you, by estimating the transit time, you can calculate the mobility. But sometimes, depending on the material, if material or your molecule is heavy, or it is not completely absorbing the light, or sometime if your charge carriers are trapped, so you get also the dispersive curve of nature. So in the linear scale, you are not able to estimate the transit time. So therefore, you are obliged to plot your photocurrent curve in the log-log curve, where you can estimate the transit time to estimate your charge carrier mobility. So here I would like to demonstrate you how it works. So before I demonstrate you the charge carrier mobility measurement, I would like to give you small information that here we use basically a Nd:YAG laser, and we have two wavelength in this laser. First is 355 nanometer, which is close to UV and visual, and second 632 nanometer. So basically, organic molecules, especially these discotic liquid crystals, they absorb the light near the UV visible interface. So that's why we use here 355 nanometer as a irradiating wavelength. And we can also adjust the pulse width, but basically 5 nanosecond is good enough. And the second factor, that is a spot size, because it is also very important that it should be exactly overlapped as compared to your active area of the material. So basically what we do, we place our this discotic liquid crystals in between the top electrode and bottom electrode. And in order to fix the thickness, we put the spacer so that the thickness of between the top electrode and bottom electrode is fixed. So basically we fill this material at isotropic temperature with a very slow cooling rate, so that the molecules are arranged perfectly arranged in the homeotropic way. Homeotropic means all the molecules are perpendicular to the bottom electrode. So the charge transport will go via this way. So what happens when we irradiate the materials with the laser light? What happens? It generates the excitons within the 10% depth of the materials. So as you know that excitons are nothing but it's a quantum bound state of the electrons and holes, but they are thermally unstable and they dissociate. So when they dissociate, they try to come over the top electrode, and they are trying to accumulate at the top electrodes. So when we apply a field, what happens due to the Coulombian interaction, that potential repel charges. So what happens? For example, if we put here the positive voltage we apply over the electrode, so what will happen? It will compel hole to go from top electrode to bottom electrode, and we can trace its trajectory, and that will be recorded in the oscilloscope. So what happens if we produce here negative voltage? What will happen? It will compel electron to go. So by recording the electron photocurrent curve or whole photocurrent curve, we can estimate the electron and hole mobility separately. So this is very a fantastic technique, because even we can calculate the ionic impurity as well, because the charge mobility of ionic charge carrier is much lesser than the electronic charge carriers. So the transient peak will be at another place. So we can estimate whether this charge transport is associated with the electronic charges or it is due to the ionic charges. So we have investigated some of the system triphenylene-based systems. So first we have discovered this triphenylene-based system. So you can see here, this is the triphenylene molecule, and depending on the role of alkyl chain, there are various homologous members of this series. So basically from HAT4 to 8, these are the 4 members in the discotic family. So these are the DSC curves. DSC, that is the differential scanning calorimetry. That is really very important to know what is the phase and where is the phase transition. So as you can see here, that the HAT 5, 6, and 8, they show hexagonal columnar phase in between the crystalline and isotropic phases. But HAT4, it shows the 2 phases in between the crystalline, solid, and isotropic. So this is the hexagonal plastic phase and hexagonal columnar phase. So this is the 2 phases. And we can determine the molecular ordering in these molecules under the polarized optical microscope. So you can see here the different optical micrograph of each of these homologous members. So here I would like to tell you that these HAT 4, 5, 6, and 8, so when you increase the alkyl chain length, the molecular ordering reduces, because the alkyl chain length and alkyl chain length nature is temperature dependent. So when you increase the temperature, what happens? These are thermally unstable, and they hinder the charge transport in this type of molecules. So we have recorded different photocurrent curves for the triphenylene atoms, and you can see here from HAT 4, 5, 6, and 8, the nature of photocurrent curve, it decreases. So if it is changed, you can also find a change in the transient time, and depending on the transient time, your value of mobility will be changed. So as I told you earlier, that the charge carrier mobility significantly depend on the molecular ordering. That's why we recorded the maximum mobility in the HAT4 and minimum mobility in the hexagonal columnar phase of the HAT8. So only we recorded in the mesophase here. So you can find one more thing important here, that the charge carrier mobility in hexagonal columnar phase is lesser than the hexagonal columnar plastic phase, because plastic phase is more ordered phase as compared to the hexagonal phase. So we have realized one more thing, that as we increase the alkyl chain length connected to the central core of the triphenylene, the molecular mobility also reduces, and it follows one empirical relation like this, which is mentioned here. And what happens, so basically only core participate in the charge transportation, but alkyl chain, they put a platform for the charge carriers, whether the path will be convenient or there will be any hindrance. So as we increase the alkyl chain length, they create more hindrance in the charge propagation, and that's why the charge carrier mobility decreases with respect to the length of alkyl chain. So these results are in revision with the Journal of Molecular Liquids. So next system we developed here, another naphthophenol phenanthridine systems. So basically this type of molecules were synthesized by Professor Sandeep Kumar at Raman Research Institute. So before we go for the charge transportation phenomena and fabrication of the devices, we analyze these molecules under the polarized optical microscope. So for these molecules, depending on the change in the alkyl chain length, we have analyzed that all four members, they show very good hexagonal columnar phase, and they represent different optical textures depending on the different molecular ordering, which is significantly dependent on the length of the alkyl chain. So there is one important demerit in some discotic liquid crystals, because sometimes these materials do not absorb a complete light near 355 nanometers. So when the laser absorption is not sufficient, it is not able to produce sufficient excitons and electrons and holes that can propagate from top electrode to bottom electrode. So what we do to cope this problem, we try to coat a photosensitive layer of PVK over the top electrode, so that this top electrode is able to absorb the laser light, and after that it injects the charge carriers into the materials, and charge carriers, electrons or holes, they propagate from the top to bottom electrodes under the particular applied voltage. So that is one problem in this. When we coat this interfacial layer, many trap states are formed, and under this condition, we do not receive a non-dispersive photocurrent curve. So we always receive a dispersive photocurrent curve. So in dispersive photocurrent curves, it is hard to estimate the transit time. So we developed a program to do the fitting, and that exactly tells where is the transit time with the percentage error of 1%. So we found that in this compound, this shows a ambipolar charge transport with the electron and hole, in which hole mobility was slightly higher as compared to the electron mobilities. So these details are communicated for publication. Okay, so now we come to move to the next system, where what we have done. As I shown you in the previous slides, that triphenylene molecules are very good, very good organic electronic materials. So what we have done in the second term, we tried to attach a phenazine part here with the triphenylene to see the effect on the charge transportation. So one of the student of Professor Sandeep Kumar, Mr. Ashwat Gowda, who is now postdoc in China, he prepared this compound. He fused this phenazine compound to this triphenylene, and he prepared the phenazine-fused triphenylene discotic liquid crystals. So it was a very good compound, and first time this compound shows that a discotic liquid crystal can show this mesophase until the room temperature. Otherwise, these discotic materials, they are high temperature liquid crystals. So what we have done here, we have performed the time of flight experiments for this compound under the different voltage and different temperature. And we found this is very good material which can serve as a organic semiconducting materials. So here we developed a program in order to measure the exact transit time for the materials, and we applied a more efficient method. We have plotted the transit time versus one inverse scale of the voltage, and we found here a slope, and the mobility is a function of the thickness of the material divided by the slope. So we estimated directly the mobility using this formula. So this is a more efficient method as compared to previous method where we were directly calculating the mobility using the formula. So one interesting result we found is in this type of compound. So as I have shown you previously that all triphenylene type of compound, they show almost temperature independent mobility. So this means mobility doesn't affect with the temperature in a particular mesophase width. So that's why here we have estimated the whole mobility as a function of temperature, and we found that the whole mobility increases with respect to temperature. So first time we have recorded this nature, and we found that um, when our molecules, they behave the growth of domain like single crystals, this nature is possible due to that mechanism. So later on, we also investigated the triphenylene system doped with the CDS nanowires just to check whether this nature persists or not. And you see here by adding the CDS nanowires into a very small concentration, the molecular ordering changes. So what we have done, we again recorded some top measurement, and you see here by the insertion of this CDS nanowire, the nature of the transient curve changes. So the value of mobility is slightly decreased, but it keeps the same nature as a function of temperature. So this whole mobility is a function of this mu naught into T to the power n, where it can be changed in the pristine system and in the doped system. Later on, we also discovered one more compound prepared by Professor Santanu Palarais and Mohali, where he has attached this triphenylene-pentaalkynylbenzene dyads in addition to this triphenylene core. And we found that it is also a very good compound which exhibit ambipolar charge transport, in which electron mobility is slightly higher as compared to the whole mobility. And one of the important thing we have observed here, when the size of molecule is heavy, it always shows a dispersive nature in the photocurrent curve. So this compound was very interesting for the organic light emitting diode, and we also fabricated organic light emitting diode using these molecules. But unfortunately, I have not shown here. Later on, we also took one triphenylene system, that is HAT4, and we dispersed some carbon and nanodots in these systems. And recently we published this in Journal of Materials Chemistry C. So what happens, as you know, that these nanomaterials, especially the carbon dots, they have the self-assembling nature, and they can be self-assembled inside any matrix, and they form a network. So what happens, we found that these carbon dots, they are creating a network inside the HAT4 matrix. And that's why they are enhancing the conductivity a lot, because all the organic semiconducting molecules, especially these discotic liquid crystals, they show a poor conductivity. So this is the problem with these materials. So it is a challenge in front of the all experimentalists to enhance the conductivity. So by adding this, we have enhanced the conductivity by 1000 times. So how we are the conductivity, mobility of the charge carrier is reduced, but only by 1%. So it's a decrease in mobility is has not been affected significantly, but we have successfully enhanced the conductivity 1000 times, and that is really very interesting for the organic electronic applications. So now I conclude my talk that these molecules, especially these Columnar discotic liquid crystal molecules, they are of much potential for the organic electronics and organic photovoltaic applications. So basically, I am running two theses with these type of materials. One thesis is focused on the photovoltaic application of discotic, and second, using these materials how to store the energy, like it is a organic batteries we are trying to do. Uh, so I must thank all my collaborators from different part of the globe, including Dr. Ambrish Srivastav, with whom we started a little theoretical work in order to put a synergy between the experimental findings and the simulation results. So I would like to thank my funding agencies because without them, it's not possible to carry forward any research work.
Yes.
There is a small announcement. The students for the master student or PhD student, if you are interested to come for any visit to France, there are various fellowship schemes offered by the campus France, like Charpak Exchange Fellowships and IFIL Excellence Fellowships and Raman Charpak Exchange Fellowships for the PhD student. So if you are interested and if your interest of research are within my field, you are welcome to apply. And normally I post most of the details over my website, so you can go to there. And there is a small announcement that we are organizing one summer school and one conference. It was in September, but due to COVID, it is postponed to December. So you can, if you want and you are interested to join this summer school and conference, I encourage you and I request you to apply to this conference and summer school. So at last, I would like to say that there is a plenty of opportunity to work with this type of materials. And at last, I would like to thank each and everyone for your kind attention and patience. Thank you so much.